So in section 1.6, we define enthalpy, which is H, to be equals to the energy plus PB. And this is the energy that it would take for you to create a system out of nothing. And of course, put it in an environment. What does this mean? Well, this is the energy that you will need to actually create the system, and this is the energy that you would need for the system to exist in in an environment. Because of course you're moving a certain volume, therefore we need to put a certain work to create that volume inside the system. So we're doing work on the system as well, so we need energy. Okay, but what if instead we ignored the change in volume for a second and we looked at the energy that our system can draw from the environment around it? Well, then the energy that we would need will be equal to the energy to create the environment minus the temperature times the entropy of the environment. And this is called Helmholtz free energy. Again, this is the energy to create the environment, and this is the energy instead drawn from the environment that helps us create the system. And this is the total energy, of course. So, what does this mean? Well, when we have in order to have this energy from the environment, we're gonna be creating entropy. So our Ts will be actually T times delta S, where our S naught will be equal to 0. So our delta S will be simply equals to S final, or we can just call S. So that means that the more entropy a system has, the more of its energy can enter as heat. So the more entropy our system creates, the less energy we actually need to create it. The higher temperature, at least, the easier it is to create this system out of nothing again. Now this of course will be the same opposite. So for example, if we were to destroy the system, the recoverable energy will be equal again to U minus Ts. But we're always thinking about creating instead of destroying. It's a little easier. However, now we can put these two things together. So we know that we have our energy to create our system, and then we can draw some energy from the environment. But at the same time, we have to make an impact on the environment by creating, by working on the volume of our system. So this altogether is called Gibbs free energy. This again is the energy of the system minus the energy we can draw from the environment plus the energy that we need to create the space that we need in the environment itself. One quick way of thinking about this is to create a table. It's a very quick table, so it won't take long. A 2x2 table where we have our U and H on our left column, and then we have F and G on our left column. So again, if you start from U and you go right, you end up with F. What do you have to do in order to get F? You have to do minus Ts. And then if you go down from U to go to H, what do you need to do? Plus PV. So if you think about this, if you go down and then right, so you have U and then you go down, so plus PV and then right minus Ts, you end up with G, exactly like in our table. It's a quick trick. It's a trick way to remember our. It's a trick to remember how all these relationship are in a table, and these four functions together are called thermodynamic potentials. Again, these are these 4 things that we put in our table. So U, F, H, and G. Now I want to go back to talking about F. So we said F is equals to U minus TS. Now, what if we have a change in F, for example, delta F, then we need to change in the components of our F, which will be equal to U minus TS. Now, these two can just be broken up in two full parts. So we have delta U minus T delta S. Now, if you remember, delta U is equals to Q plus work. So we can substitute it in here. And so we have that Q plus work minus T delta S is equals to delta F. And when we have no new entropy created in the process, then we have that Q is equals to T times delta S. Because again, Q would be the energy that goes into creating new entropy, but we have no new entropy, so all the energy can pretty much just cancel each other. And therefore we have that delta F would be equals to work. However, this relationship that we wrote right here is not always true. Since we know that we're always going to create some entropy, so we know that delta entropy is greater than 0, then Q will be less than T times delta S, and therefore our delta F will be less than or equal to Q. So this is for a constant temperature, of course. This is pretty straightforward, and we can do the same process for delta G. So again, or Gibbs free energy. So we would have delta U minus, actually only plus, minus delta T delta S plus P delta B. We can substitute again our delta U because we said it's equals to Q plus work. So it's equals to Q plus W minus T delta S plus P delta B. Okay. Now again, we can cancel out Q minus T delta S. And we're left with W plus P delta B. However, our work is equals to negative P delta B, because if you remember, if we have an increase in volume, then we have a negative work. You can think about it, you have to do some work to decrease the volume of a bottle full of air. So then you need to do work to decrease the volume. Therefore, if you let it increase, we're doing negative work. Plus work done by other. So for example, we have electrical work done on the system. Therefore, we substitute in here, we're going to have minus P delta B plus work of other plus P delta B. So these two cancel out, and we end up having that delta G is equals to work of other. But again, we always know that we're not going to have a perfect Q is equals to positive T delta S, and we're going to have a Q actually less than T delta S. So our final delta G will be less than or equals to work of other at a constant, we're always assuming, temperature and pressure. Because as you can see in our initial formula, temperature does not have a delta, and as well as pressure. Neither of them has a delta. And this is pretty much the whole point of the chapter. There's some reference to what's going to come after, but it's not really useful for now. So this is it.